Welcome to my video course on engineering FRMCS. Today, we're diving into a fundamental transformation in how modern railway systems actually operate. We're going to explore how the industry is severing those rigid historical ties between railway applications and the underlying radio technologies. This explainer is going to break down the sheer engineering brilliance behind this absolutely vital decoupling.
All right, here is our course syllabus for today. We'll be covering the legacy challenge, the architectural shift toward modularity, our core interfaces, practical usage and APIs, coupling modes, and finally, the future of rail. Let's jump right in.
Section 1. The Legacy Challenge, Tightly Bound Systems. To really grasp the brilliance of the new design, we first have to understand the major structural constraints of the old one. Historically, legacy railway applications were completely forced to speak the specific, nuanced language of whatever transport network they were running on. Think about previous generations of rail communication for a second. They relied heavily on modified commercial technology, requiring bespoke equipment and custom software just to deliver specific railway functionality. And honestly, this tight binding was an absolute nightmare for system upgrades. If the telecommunications network needed to change or evolve, the train applications essentially had to be completely rewritten too. The hardware, the software, the interfaces, they were all inextricably linked, making modernization incredibly slow and exceptionally expensive.
Section 2. The architectural shift, true modularity.
Okay, let's consider the clean, physical, and logical separation at play in this new architecture. The railway application stratum now sits completely independent of the transport stratum, with the service stratum acting as a crucial buffer right in between them. What does this actually mean? Well, it means the transport network, whether we're talking 5G, Wi-Fi, or eventually 6G, is now just a dumb pipe. Its only job is delivering data to the application. The days of monolithic, deeply integrated architectures are totally gone, replaced by strict, uncompromising modularity. It completely insulates our critical railway applications from the underlying telecommunication mechanics.
Section 3. Core interfaces, the universal translators. So to make this modularity work, we have two absolutely critical reference points. First, the OBAPP, which stands for Onboard Application, and second, the TSAPP, its trackside equivalent. You can think of these as standardized universal adapters. They are essentially gateways. They allow vital applications like the European Train Control System or automatic train operation to plug straight into the network. And because of these standardized reference points, the application itself literally doesn't need to know if the underlying network is 5G, a satellite connection, or public Wi-Fi. It just talks directly to the OBAPP or TSAPP, and the communication system handles the rest.
So the really crucial point here is understanding how these interfaces actually manage the data. They're divided into two distinct logical planes. First up, we have the control plane. This acts as the administrative layer. It handles application registration to the system, authenticates identities, and manages the requests for different services. On the flip side, we have the user plane. Once all that administrative setup is completely finished, the user plane steps in to handle the actual heavy lifting. This is the flow of IP packets, the voice communication, and the video data that's constantly traveling to and from the applications. Section 4. Practical Usage and APIs, FFFIS specifications. Now, let's think about how this practically maps out. The OBAPP and TSAPP sit right smack in the middle, perfectly placed between the application's functional needs and the network services. And how do they communicate? They expose functionalities via standardized APIs. This is a total game changer. It means a developer who's creating a new train control application doesn't have to code for specific radio frequencies or 5G data link protocols anymore. No way! They simply code directly to the standard API mapped out in these specifications. It creates a beautifully seamless, standardized bridge right across the entire railway ecosystem. To be specific, these APIs offer a really robust set of capabilities directly to the developer. Through the OBAPP, applications can easily request data flows for voice communications, standard IP data routing, and even high-bandwidth video streams. Crucially, the interface also provides built-in capabilities to guarantee the integrity of those data flows as well as their confidentiality. The real beauty here is that these API capabilities are entirely generic and completely network agnostic. Let's walk through how this builds into a highly secure operational flow. Before a single byte of data can actually be transmitted, applications have to pass through a critical security gate, which we call local binding. Step 1, the application requests network access. Step 2, mutual authentication and authorization take place via the OBAPP or TSAPP, using pre-configured credentials. Only when this registration step is 100% successful, which brings us to step 3, are the actual communication services unlocked for that specific application. It's an airtight process that ensures a highly secure, tightly controlled environment on the train.
Section 5. Coupling modes. Achieving technology independency.
This concept right here really highlights the core philosophy of modern rail communication architecture. Telecommunications technology independency is not just a nice-to-have, it is a mandatory requirement. Because of this, certain railway applications simply do not directly use mission-critical or MC service primitives from the transport layer. Instead, they operate in what we call a loose coupled mode. In this mode, applications exclusively use standard API primitives rather than the core network primitives. This is absolutely essential because it guarantees that if the core network gets an upgrade, the application remains completely untouched and safely future-proofed.
But hang on, what about legacy applications? Or generic off-the-shelf applications that know absolutely nothing about this new rail architecture? Well, that leads us to a brilliant engineering trick called the super loose application regime. In this regime, the application itself is completely in the dark. It's totally unaware of the OBAPP or TSAPP. Instead, an intermediary agent handles all the interactions, all the registrations, and all the API calls on behalf of the application. Basically, it acts as a proxy. This is a massive advantage because it means you can integrate almost any generic application into the ecosystem without having to rewrite a single line of its core code.
Section 6, the future of rail. Lesson wrap-up. By cleanly decoupling the application from the transport network using these OBAPP and TSAPP interfaces, the railway industry is unlocking massive industry-wide cost savings. We're talking seamless network upgrades and the rapid deployment of brand new data-hungry applications. So I'll leave you with this final provocative thought. As transport networks inevitably evolve from 5G to 6G and beyond over the coming decades, will your beautifully decoupled railway applications even notice the upgrade? With this level of strict architectural separation, the answer should be a resounding no.
Thanks. We can see you next video.